This video is for section 2.5, which is the topic of limits involving infinity. Okay, there's a couple different types of limits involving infinity, so let's go through them. The first one is infinite limits. We can conclude that the limit as x approaches 0 of the function 1 over x squared, which we used in the last video where we were discussing continuity, is approaching infinity. By observing from the table of values and the graph here on the right, that the values that we enter as we get closer and closer to 0 on both the left and the right side are approaching really big numbers. And again, we did this when we were trying to show that there's a discontinuity at 0 in the other video on continuity. So the limit, because these are both approaching the positive infinity from the left and the right, then the limit exists, or the limit is infinity. We actually consider this limit not existing because it doesn't approach a value, but since it's going to infinity and it's not necessarily undefined, then we would say that the limit is equal to infinity. Okay, pretty much I just said that. Here's the symbols that we would write. The limit as x approaches 0 of 1 over x squared is equal to infinity. Or in general, we'd say the limit as x approaches a value of a function can be equal to infinity. It can also be equal to negative infinity if they were going down towards negative infinity. Okay, the notation here means that the values of f of x can be made arbitrarily large. Arbitrary just means any number, really, really big. It's almost like random. As large as we please by taking x sufficiently close to a, which in the last example, our a value was 0, but not exactly equal to a, because as in our last example, when we were actually at 0, the function was undefined. So it wasn't continuous, but it did have a limit. Again, the symbol, which looks like an 8 that fell over on its side, is called the infinity symbol, is not a number. Really important to understand that infinity is not something you can put your finger on and say, I know what infinity is, it's this value. No. Infinity is just like a placeholder. It means that we are looking at a number that is really, really unimaginably big. So English-wise, these are what we're saying, the limit of f of x as x approaches a is infinity. It's good for you to know how to translate mathematical symbols because again, as us mathematicians, we like to write very concisely, but we also need to make sure that we know how to read our symbols. All right. Similarly, as shown in the picture below, the limit as x approaches a of the function that's in blue is equal to negative infinity because notice as we approach a from the left and the right, we are going down instead of up, which means we're getting to a negative infinity. Negative infinity is also not an actual number you can place your finger on. It is a really, 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 really tiny number. The symbol limit as x approaches a of a function is equal to negative infinity. We already read it. We have an example. Same example that we used for positive infinity, except the negative side in front, which will give you a graph that looks like this. Okay, so we have left and right limits that can also be infinite, and that's okay. Sometimes we have functions who are only going infinity on one side, and there is no other side because there's an asymptote and then the function stops. So the limit would exist in that case. But remember, if the left limit, does not match the right limit, say they're going in opposite directions, then the limit does not exist. The left and the right have to be the same in order for the overall limit without direction indicated to exist. Let's find the limit of the following. So if we were to look at the function 2x over x minus 3, and we approach 3 from the left and from the right, we are looking for what that derivative would be. Derivative, oh man, it's late. What that limit would be. So let's do this one graphically. I'm going to put in my calculator 2x, I'm going to put in parentheses, 2x and then my y equals divided by x minus 3. Show you what I'm doing. So here's my y equals. And then I'm going to hit graph. Let me just expand my x-axis because I feel like I can't see the other side. Oh, there it is. Let me fix my window. Ah, that's better. Okay, so here's the graph that I'm looking at. Let me draw for you exactly what is happening at 3. So we are looking at this graph. If you graphed it in your calculator, you should be able to see this. But the function coming from the left approaching 3 is dipping down. So, and the function as we approach 3 from the right is up here. Ooh, that's a little far over. Let's try that again. It's got to go. So if we approach 3 from the left side, we see that we're approaching negative infinity. And if we're approaching positive 3 from the right side, we're approaching positive infinity. So since from the right, we're approaching a really big number, and from the left, we're approaching a really small number, then if we were asked to find the limit as x approaches 3 without a direction indicated of this function, we would have to say that the limit does not exist. And the reason is because they are not approaching the same values from the left and the right, which is the classic definition of limits not existing. The left and the right have to be the same. The graph of the curve, oh, and here's the graph of the curve. So we can see that's exactly what I was trying to demonstrate. Let's take a look at limits at infinity. So in computing infinite limits, we let x approach a number, and the result was that the values of y become arbitrarily large, positive or negative. Here, we let x become arbitrarily large, positive or negative, and let's see what happens to y. Let's begin investigating the behavior of the function defined by x squared minus 1 over x squared plus 1. So the table at the right gives you the values. Notice that we can write the x values with the plus or minus when we're working with a symmetrical graph, because the y values are the same coming from the left as they are coming from the right, especially when we are focused on this value of 0. So the symmetry, it's the line of symmetry, so that's why this works out the way that it does. Now, we are looking out to infinity. So if I'm looking out to positive infinity on the x-axis, so if I'm asking you, what is the limit of this function as x gets really, 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 really big, you're seeing that it approaches the value of 1. I'm also could take the limit as x approaches negative infinity, and that limit would be equal to 1 as well. It's going to be equal to 1 on both sides. So let me show you what that looks like written. So what I'm saying is if I take the limit as x approaches positive infinity of, I'm just going to call this function f of x so I don't have to write it out. So this function here is f of x. It is equal to 1 as we're going off to infinity. And I can also see that in this chart, I'm approaching 1, getting closer and closer and closer to 1 analytically, and graphically, I'm seeing the same thing. So we can also say that the limit as x approaches negative infinity, notice that we're approaching really big values here, of the function is equal to 1. So I'm approaching 1 whether I'm approaching really big numbers or really small numbers, or big negatives, as I like to call them. And that's us approaching affinity on the x-axis and looking to what value on the y we're approaching. Okay, we covered that slide. In general, we use the notation the limit as x approaches an infinity of a function is equal to L, where L is a value, the limit. So here, as we approach positive infinity on the x-axis, we are approaching some limit L. This is another example of how we can approach a limit with a horizontal asymptote as we go very far out to the infinity. And this display shows us that we don't necessarily have to have an asymptote that's like an imaginary wall that we'll never cross. Sometimes we have these limits that it almost looks like a path of a ball bouncing, where a function will bounce, but it will look like gravity's taken its toll and it's getting a smaller, 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 smaller bounce. So it's approaching this midline. Again, the symbol negative infinity doesn't mean a number. It means a really, really small number. And as the limit of x approaches infinity of f of x is equal to L, and the x equal approaching negative infinity is also equal to this limit L, we are saying that L, the horizontal line, y, oh, I'm so sorry, y equals L is called a horizontal asymptote. The curve y equals f of x that's sketched below has both an y equals -1 and y equals 2 horizontal asymptotes, because as we take the limit as the function gets really big on the x-axis, approaches positive infinity on the x, we're approaching a y value of -1. And as we go in the opposite direction and we take the limit as x approaches negative infinity, we are approaching a y value of 2. So note that you can have horizontal asymptotes where not the entire function follows the rule. In this case, this function crosses through this imaginary wall in this general area, but it's a horizontal asymptote for this general area. So that's something that you may not have known, that asymptotes don't always have to hold true for the entire function. Sometimes they're locally true. Let's find the infinite limits, limits at infinity, and asymptotes for the function of f who's drawn in this picture. Alrighty, let me switch over to my pencil here. I think we're going to do green. So I'm looking for, let's first do, we're approaching x values and the limit is going to infinity. So here, as I approach the value of -1 on the x-axis, my graph limit is going to positive infinity. So one infinite limit that I see is that the limit as x approaches -1 for this function drawn, we are going to positive infinity. It is getting really, really big. I also see that coming from the left side and approaching 2, I am going to be going to negative infinity. And if I approach 2 from the right side, my limit is going to positive infinity. So let's write those out. So I have the limit as x approaches 2 from the left. I'm approaching negative infinity. And if I take the limit as x approaches 2 from the right of my function, I am going up to positive infinity or a really, really big number. Okay, so those are the three places where I see us approaching a value on the x-axis, but the limit itself is infinite. Now let's take a look at where we are approaching infinity on the x and then approaching a value for the limit. So if we are going to approach negative infinity on the x-axis, I can see that the limit is 2. And if I approach infinity on the x-axis, then my limit, it looks like it would be 4. So I'm going to write that out. So we take the limit as x approaches negative infinity of this function is going to give us 2. And if we take the limit as x approaches positive infinity of our function, we get 4. And those are the infinite limits that we can identify here. What is that line for? Random line. Let's erase the random line. Okay. So then the last part of this question is asking us to identify the asymptotes. So we have a vertical asymptote at -1. X equals -1 is a vertical asymptote. We have a vertical asymptote at +2. We have a horizontal asymptote locally, applies locally, here at y equals 4. And we have a horizontal asymptote here locally at y equals 2. Now let's talk about infinite limits at infinity. The notation, a limit as x approaches infinity of a function is also equal to infinity. It can be negative infinity, positive infinity combination, or both in positive, both negative. Let's take a look at some examples. So we have the limit as x approaches infinity of the function, the exponential function e to the x is equal to infinity. Take a look. So as I'm going to the right and I'm approaching really big x values, my y values are also getting really, really big. Same thing here. As I approach positive, I go positive. Same thing here. Approach positive, I go positive. Now, if I am approaching negative infinity on the x, notice it looks like I do have an actual value of a limit of 0 going this way. But for this one, if I approach negative infinity on the x-axis, my y values are also approaching negative infinity. Let's take a look at this example. Now, for this example, I see that I cannot do a direct substitution when I'm working with infinite limits. As if I put infinity, essentially what I'm going to end up getting, and let me use my pencil for this one. If I make a substitution into this rational function, what I end up coming out with is infinity over infinity, which we're going to learn that this is called an indeterminate form. An indeterminate form does not conclude anything. It doesn't mean it doesn't exist. It doesn't mean it's undefined. It literally tells us nothing. We know nothing. That doesn't mean stop and say there's no limit. No, we literally know nothing. We have learned nothing about this limit. So it just means you need to take another approach. Erase. Nope, my erasing didn't work. My erasing didn't work. All right, clearing out. Let me show you how to do a limit like this one. The best way to do this, you can use your algebraic methods that I've taught you in a previous lesson, where we factor and we try to reduce algebraically. But remember, it's not always possible to factor polynomials. Not all polynomials are factorable, and not all of them are really easy to factor either. So there's another technique we can use. Now it's important you remember which of the highest power to look at. Identify the variable to the highest power and very specifically in the denominator. We care about the denominator, not the numerator. So I see that 5x squared is or not really the 5, x squared is the highest power in the denominator. Now remember, when we're working with expressions, which means we don't have an equation here, there's no equal sign, we cannot change the expression by multiplying by anything but 1. We multiply by 1, we should know that multiplying by 1 does not change the value of a function. So I'm going to strategically multiply the top by 1 over x squared, 1 over the highest power of the denominator, over multiplying the denominator by the same thing, 1 over x squared. Now, although this is a very complicated form of 1, technically it's 1. I have 1 over x squared over 1 over x squared. Same thing over the same thing, 1. So now what this is going to look like when I multiply through, we still have to take the limit as x approaches infinity. We haven't taken the limit yet. But we'll have 3x squared over x squared minus x over x squared minus 2 over x squared. Because again, we multiplied dividing by x squared through the numerator. Same thing for the denominator. So this is all over 5x squared over x squared plus 4x over x squared plus 1 over x squared. Now let's simplify before we do anything else. So x squared over x squared will cancel. We're just left with 3. This will reduce to 1 over x, and the 2 over x squared will stay. X squared over x squared, we're just left with 5. This reduces, and the 1 over x squared would stay. That gives us, we still have not taken the limit yet, so we shouldn't drop the limit as x approaches infinity, because I noticed that many students, if they drop that, writing that piece because they're lazy, or they, not necessarily lazy, but they're just trying to focus on the algebra right now. But what happens is they forget to do it in the end because they stop writing it down and then they get stuck and they don't remember where they're at. So it's in your best interest to keep writing the whole problem for every step. So we're left with 3 minus 1 over x squared minus 2 over x squared. Ooh, my apologies. This middle term is not x squared, it's just 1 over x. Over 5 plus 4 over x plus 1 over x squared. Now something cool is going to happen. Let's actually take the limit. So when I take the limit, every x is a really big number. Think about this. If you have a fraction with a small top and a really, really big denominator, what number is it close to? Like 1 over 1,000, or 1 over 1 million, or 1 over 500 million. That's right, you're really close to 0. So we consider any constant divided by infinity to be a number very close to 0. So that means that this value is 0, this value is going to 0, this one's going to 0, this one's going to 0. We have all those terms going to 0, leaving us with the limit approaching 3/5. Now, if we graph this limit, we should be able to see that it is approaching something right before 1. On a calculator, it would not be that obvious, exactly the limit of 3/5, unless you did it analytically and put it in the table. But again, the table would be very difficult for you to identify 3/5 because our tables are typically in decimals. And it's very unlikely that you know what the decimal is for 3/5. I mean, you could check, but going backwards, it's not that easy to find out. So I'd strongly recommend this method, which we will use more than one time. It will come back up, and it is a very, very easy way to alleviate indeterminate forms, especially when you're working with rational functions, and get your limit quite easily. Okay, this concludes our lesson on infinite lesson. Oh my gosh, I'm tired. Infinite limits. I'll see you guys next time.